Are you? Got that upgrade. Yeah. Thanks. All right. Introduction?
No, oh yeah, yeah.
I can start. That's all good.
Yeah, we'll hold off a couple of minutes.
What a day again. When are we getting rid of this rain?
Usually like, what are we in March or so? Kind of our
Beginning
spring
of-
break, like 2 or 3 weeks. That's usually when it turns off.
So Stanford kind of knows when it's spring.
Yeah.
Turns the shuts down the rain.
And that's pretty dry till from then until like September. So,
Okay. No, I'm happy for the environment, just
Yeah,
not
yeah.
for my own.
yeah, get around, sure. Yeah. 3 years ago, we had a super dry winter.
Yeah, and that's how the wildfires start.
Yeah.
It's good that it rains. Just
It seems to go
But
like a
continues.
cycle. I find over being here many years. It seems it's like 2 or 3 years of rain, 2 or 3 or 4 years dry.
Yeah, hopefully it's not a trend.
Yeah.
We don't want
Well, when I was a student at Berkeley, they were talking about drought. They put in extra water lines across like San Rafael Bridge, so it was like severe drought. When rains came. So it's not a new thing.
Oh, I see.
At least that. Okay, I guess we'll get started. So I think some of you know Serdar Selaman. He taught he's visiting here from Turkey this year, and he's kind of taught last fall the course on structural fire engineering. He did his PhD and he does research in that area. So anyway, we thought we'd take this opportunity to have him give a module, kind of in the spirit of some of them that we've had from that Francisco Galvez has given, of looking at nonlinear analysis applied to structural fire engineering. So anyway, so Serdar's going to put on this module. Everybody got my email, so I see you have your laptops there. We do have like an exercise, and I think as I mentioned last class, the last exercise we did with Quofem to do the calibration and the exercise that Serdar will do today. We'll kind of put those out as an assignment. That it's going to be an optional assignment, so you can focus all your remaining energies on your projects for the next week or two. But I would encourage you to go back and kind of complete these, because it's pretty powerful to see. And we're going to be using OpenSeesPy again, how you could really do something that just a few years ago was like unapproachable for most, certainly practicing folks who aren't specialists in the field. So anyway, thanks.
All right. Thank you, Greg. Again, thank you very much for this opportunity. I had this opportunity to give educational fire engineering class or structural fire engineering class last quarter. And this module will be pretty much because it's a highly nonlinear problem. Fire engineering or structural fire performance is a highly nonlinear problem. This module might give you a little bit of an insight who has not been able to take my elective class last quarter to have a glimpse of what's really happening when the structures are affected by temperatures. And it also gave me an opportunity to learn, how to do, write code on the Google Colabs. I think Colab, it's a great opportunity to be able to do this online in front of the class, because usually what we do for this type of structural analyses, we use OpenSees, but we use, we write article code and we submit our work, get some results, put it on Excel and try to show it to class. But this is much more interactive. So I had this opportunity to learn as well. So it's going to be good. What I'm going to do for this class is I'm going to go through some highlights of structural fire engineering and what it entails and how is it really different to what you guys are studying. You're studying nonlinear and how to do nonlinear analysis, and mostly earthquake. So it's going to be a little bit different, but not too different in terms of mathematics involved. And we're just going to be dealing with temperature rather than accelerations exposed, ground accelerations affected to the structure. And then I will be looking on 4 different codes that are going to be, 2 of them will be on validation, quite simple, straightforward codes. And the other 2 will be a effect of boundary conditions on a simple supported beam element, and also effect of loading, gravity loading that's when the beam is subjected to fire, the gravity loading will also have an effect on the behavior of the structure. So I've written down these things on the board. So these are the case studies we'll do, beam exercise 1 and 2. And the fire will exposing it, it's going to be having heating for the exercise that we do. But I will also go down with an example with the cooling through the PowerPoint presentation. And the validation will be, as you will see, that it's going to be something that we need to do every time we run fire. Well, any type of nonlinear analysis, but for fire, it's important because the material behaves and it will become a different material at every different temperature. So we have to make sure that the material that if we input is certainly doing what we expect it to do, because without the material validation, the performance of the structures will be something that we need to be really careful about. All right. So fire engineering overall has 3 different pillars. And the third one is going to be the one that we will be focusing, thermomechanical analysis, but it actually starts with the load. And here the load is the combustible materials, okay? And they do create this environment in a building or in a structure, mostly indoors, but it could also be an outdoor structure. So it could be a bridge, for example, a suspension bridge that's affected by fire. So those combustible materials increase the temperatures of the environment, and those increased temperatures infuse into the cross sections or into the structural elements. They elevate their temperatures, and the material behaves differently. There will be P delta effects as well, and geometric nonlinearity effects as well that affect the structural performance. The second part is the heat transfer that I said. So basically, from the gas temperatures, the structural temperatures. That transition is governed by Laplace elliptic partial differential equation. Some of you, if you have taken heat transfer class, you would know this, partial differential equation that we need to solve. But essentially, whatever you put as a gas temperature, it's not going to be, exactly the same temperature of the structure. So there will be a phase, there will be a delay, and the structure will not absorb all the heat that's actually in the environment. It really depends on its profile and material properties. And the last one is a thermomechanical analysis. So once we have the structural temperatures ready at hand for the entire span of the structure, then we can just assign those temperatures to the structure and see how it behaves. So it does actually simply put, it does 2 things. When you increase the temperatures of the structure, it elongates. When you decrease it, it contracts or shrinks. That's from elemental physics. But on top of that, it also the material, it's the load-bearing material, either steel, concrete, or timber. It actually changes its mechanical or stress strain curve. So whenever you have high temperatures, the stress strain curve of these materials also change with time or with a given elevated temperature. So first of all, fire is a load on structures. Here are some examples of high-rise buildings. It doesn't just cause non-structural damage. It actually does cause structural damage. And some of these buildings doesn't happen too often, but they end up being demolished, and it causes a big problem unless we do our knowledge check ahead of time. And what do we do about this? Traditionally, we have to apply, if the material we think that is vulnerable to fire, such as in steel, and this class I will be talking, focusing on steel only, because the examples will be also on the steel beams. We protect them against fire. How do we protect them? We make sure that they're covered with a material that has a very low conductivity, very high specific heat. That means that it absorbs the heat, but doesn't translate into the structure or into the material, the load-bearing structure. But we cannot obviously do this forever. We have ratings. We can keep the heat or the temperature below a certain threshold of the structural member for 30 minutes, for 60 minutes, for 90 minutes, or for 120 minutes. Usually those are the fire ratings, we call them. We cannot do it forever, but we can delay, their temperatures to elevate, even if the environmental temperatures are at quite high levels, we can protect them against that heat condition. This is a fire board, usually made out of gypsum, which again has this property of keeping the heat, away from the structure member inside. But architects don't like this because it doesn't expose the steel section profile, and you actually just see boxes. And usually this was an old-fashioned fire protection, but quite, I would say, conservative fire protection in the old days. This one, I'll show an example. This is a spray protection. It's still quite commonly used. The spray is a cementitious or gypsum-based material, and you need to apply. It's a very dirty job, but in the end, it is a fire protection material that's being commonly used still today. And I will also show you an example from this campus, the School of Education. I think is this. It's nearby the Green Library. You'll see that spray protection is applied. I think this is. So you can see the second and the third floors. The spray applied protection is applied to the steel members. The first floor, I'm not sure why it's still not protected. Maybe there's another occupancy type that they're thinking of doing, and they might apply something else there, or maybe it's just in the process. But it was a good opportunity for me to take this picture while you can see the differences. So one is a bare steel, the other one is spray applied protected steel. Here's a zoom up to this. So you need to make sure that you measure, because it's a very, so that you're just spraying. So you have to make sure that you're accurate with the thicknesses that you have that spray. And it pretty much hardens right away, but it's still a semi-fluid, viscous material. So you need to make sure that the thickness is pretty much uniform across the board. And these thicknesses are determined by us, structural fire engineers. We need to make sure, knowing what the fire load is and knowing what the fire rating is, we need to make sure how much thickness that we have to apply. Another protection is blanket protection. This is actually quite expensive protection. These are actually ceramic nails, which are also fire resistant. But it is generally used in fire testing. So for, when you do fire testing of a structure, you don't want some parts of it to be affected by fire, let's say connections, for example. You don't want the structure to fail completely. You want some part of it just exposed to fire. And then the remaining part, you're, wrapping it with a blanket, which could be made out of mineral wool. Again, it's a very heat resistant or heat transfer resistant material that protects the steel. This one pretty much dominates the market at this point, which is called intumescent paint protection. It's not a recent development, but it's been here only for I would say maybe 20 to 30 years. And it is a paint. It's very thin. You can think of this as a corrosion paint that you apply on steel. And but this paint has a special property. It swells when it's exposed to high temperatures. So what happens is when it swells, its thickness increases, and it is already a very good material for fire protection. And then again, it basically makes sure that the heat doesn't travel as fast inside the steel. And it looks aesthetically pleasing because it's just paint. It could be any color. So imagine that you would be applying intumescent paint on this bare steel, and you can keep this color and it will just look good, or you can just change the color. But it is expensive, and it doesn't protect at very high temperatures. For example, if you have temperatures reaching up to 900 degrees, it actually starts to fall off. So it doesn't have a very good, it's not sustainable for a long time if you have severe fires. Okay. And why this is popular is because in the States, for example, we rely on sprinkler systems. So sprinkler systems are supposed to extinguish the fire when it gets to very high temperatures. You can have like 300, 400 degrees, but after that, the sprinklers will, get activated, and the remaining temperatures will be below what you would expect. And this is a very good material for that. But if you don't have a sprinkler system, or if your sprinkler system somehow fails and you have a very high temperatures for a long duration in the structure, then intumescent paint is not the way to go. Standard fire is pretty much what we use. It's one fire curve. The equation is written down there as well as on the board. It's a curve that we use in our prescriptive approaches. Although this class, what I'm teaching here is mostly performance-based, so we're actually analyzing, we're doing nonlinear analysis, so it's a performance-based approach to fire engineering. But 90% of the time, structures that you look at as a structural fire engineers, you do prescriptive design. And this is, way back when, this is early 1900s, when this fire was developed. It's a cellulosic fire. That means that you're burning wood type of material, which is combustible, and you have almost infinite amount of fuel load. And that's the reason you get a monotonically increasing fire temperature. Pretty much, it goes asymptotic, but it just increases maybe 1 degree at a time, but just continuously forever. So it's a logarithmic function. And you can see that it has a very fast, these are in terms of Celsius. So you reach to 500 Celsius within 5 minutes, which is pretty much not, in real life, you will not have a fire that starts, and unless it's an explosion, within 5 minutes, you reach like uniform 500 degree Celsius when this roof works. But the purpose of this standard fire is not to mimic what's really happening. It only mimics, or it only tries to simulate the fire phase when it's structurally significant. Meaning that you have a fire that's starting on the corner, and it develops, it reaches to a certain point where it becomes structurally significant. That's when we reset the time here. Okay, so the first 5 minutes is actually, there might be another 30 minutes before that, but we don't really care about that as a structural engineer. We have to care about it as a fire engineer, because we have to think about evacuation and other things. But for structures, it's not really significant if you have a temperature which is 100 degrees, or even 200 degrees. That's not a significant fire for structures. It doesn't really affect its performance drastically. So we're pretty much, this is called post flashover fire, or structurally significant fire. There are many things that are not good about this fire curve. Performance-based structural fire engineers will always, complain about this fire because it's not realistic. It's always monotonically increasing fire. There's no cooling effect, which is very important to structures. It's just one type of fire. What is the likelihood that you're going to get this kind of severity of fire in every building? Some buildings might have a fire load which is much larger than this. Some buildings might have a fire load which is very, very small. So why do you design for a very significant fire curve like this if most of the time it's very conservative, too conservative? Okay, it's like building castles. If you're an earthquake engineer and you don't want to do a nonlinear analysis, you just build castles with last for 1,000 years, and you say, like, I designed a safe building. Yes, you have, but you were not being cost efficient. You're not applying your knowledge. It's the same thing here. This curve has been developed when there was not enough fire science available, and also structural. Elliptic partial differential equation, also called Laplace equation. It's a second order partial differential equation with respect to temperature that depends on the time component of the temperature. So the increase of the temperature with respect to time in this outside environment, and this part here is all material properties. You can see the density rho. C is called specific heat. It's the amount of energy that you need for 1 kilogram of material to heat its temperature by 1 degree of Celsius. So it's a very simple formula that's a material thermal property that's being used in heat transfer. So if the specific heat is high, that means you need more energy to increase a material temperature. These are the fire insulators. So if you need a fire protection material, it has to have a very high specific heat. The division is by the conductivity K. As you know, the metals are highly conductive. So steel is a highly conductive material, which might not be good for fire conditions. For example, as opposed to concrete, which is almost 1/50 less conductive than steel. So that also creates other problems, but we're not going to discuss those. But in the end, you have a material property, whether it's steel, concrete, or timber. You have a temperature change with time within the structure that is on the right-hand side. On the left-hand side, you have spatial coordinate, so basic partial differential equation of the temperature with respect to X, Y, and Z. Or you can have a two-dimensional heat transfer problem, one-dimensional heat transfer, or three-dimensional heat transfer problem, depending on the complexity of the problem that you'd like to solve. For steel, we will go through the conductivity and specificity that are temperature dependent, but the density of steel, as you guys would know, is 7,850 kilograms per meter cube, and that stays constant throughout the fire, obviously, because it's not an organic material, so it's not losing any water, anything like that. So the conductivity of steel is it starts with 55 watts per meter per Kelvin. So again, watt here is the heat flux. You can think of this as power, okay? But in this case, it's actually energy multiplied by time, divided by meter per length, divided by, again, by Kelvin. Of course, you can think of this as Celsius. And that conductivity will drop as we go at higher temperatures, and it will stay pretty much constant after 800 degrees. And I think this range is already a very, very dangerous state for steel to be in. So we have to make sure that most of the times we have to keep the temperature of the steel member below 800 degrees in order to have a functioning structure. And why is it decreasing? You can think of this as you can think of the heat as molecular vibrations. So as the molecular vibrations increase, as the material heats up, it decreases the mean free path of molecules. So basically, conductivity is, transfer of heat from one molecule to another. If things are jiggling much faster, it actually makes it difficult for the heat to transfer. The flow of free electrons will be obstructed. Sometimes you don't have the opportunity to use temperature dependent conductivity. Maybe your code doesn't allow that. You need, some simplistic codes, you have to use a constant variable. So you can just use something along 45 watts per meter per Kelvin in order if you just want to do back of the envelope calculations to see what the initial calculation will yield. Specific heat, on the other hand, will start at around 425 and end at around 650, but it does have this this peak, this spike, which only occurs when the steel changes its phase, and it's due to a metallurgical change from Fahrenheit pertite to Osterite. So we don't have to know about all this, chemical engineering or metallurgical problem, but we know that because of that phase change, it becomes harder to increase the temperature of steel. Okay, it requires much more energy in the sense of, I would say, 10 times more energy that you require, which could be good. It is a good thing for, if you reach to those temperatures, then at least there's some stalling moment for the steel temperatures, even if you just input so much energy into it, energy meaning that you so much heat into it, it just doesn't increase its temperature. So it's a good thing in the sense that it's keeping its temperature at least the rate of increase is stalling. But at the same time, it's numerically a problematic problem, right? So if you're trying to integrate through time and you get this spike, it's a problem numerically. So you need to make sure that around this temperatures, you have smaller times. You use smaller time steps or smaller temperature increases to capture this correctly and also not to diverge or to be able to converge. Any questions so far? Okay. Last thing I would like to talk about is the thermal elongation. This is a purely mechanical problem because this thermal elongation, which is also called free strain, it's a strain or it's an elongation if the boundary conditions are free, will not create any mechanical stress in the structure, okay? And has to be considered in any fire situation. But if we impose boundary restraints in any direction of the degree of freedom in our structure, then this elongation will actually be converted to a stress. Not fully, depending on our restraint. If it's a partial restraint, some of this elongation will be actually the deformation that you see in your structure, and some of it will be actually observed by as a mechanical response. So here we call this problem as thermal induced stresses, because when we have elongation and when we have some partial restraints, we are actually increasing the stresses in the structure, which are not due to gravity load or any load that we put in the beginning. They are actually thermally induced, created by the temperature itself and the proper geometric conditions of the problem. Okay, so and it comes from the compatibility. So maybe I can just write that down too. So when you think about let's say you have an axial restraint which is full, so that means that in the end you will have a deformation that should be equal to 0 at the end of the beam. This you can think of this as a beam like this. The axial deformation here, unless you have like vertical deflection, it should be equal to 0. So that will be compatibility. That means that the thermal strain, which is part of this elongation, plus the mechanical strain should add up to 0 at the end of your boundary condition. So that means if you're exposing a thermal strain, that number should be negative in order to be equal to 0. So that means you're actually creating compressive stresses due to strain in the negative direction. You're actually compressing the material, and this is just one very simple compatibility problem that we need to take a look at. Well, of course, this 0 could be also a function of the boundary condition itself. And lastly, I'd like to talk about the changes in the mechanical response. So this, and obviously the stress that depends on the mechanical strain. So that also changes with respect to temperature. At every different temperature, especially at high temperatures, this is a stress strain representation of steel according to Eurocode. We know that we can simplify this much. For example, for ambient condition steel behavior, you can just think that you have a strain-stress curve, which is going to be linear up to a point. You might get a little bit of a either perfectly plastic, elastic perfectly plastic material behavior, or some sort of a strain hardening. Okay. And then at some point it will rupture, or you can also model the descending branch. So this is at ambient temperatures. But at higher temperatures, this range where you can have constant Young's modulus will change. And maybe you might have still the same yield stress, but it will definitely behave much more nonlinear, meaning you have to solve for tangent modulus at every time step. Okay. So it becomes like I would say concrete behaves like this, so it's a lot more nonlinear in terms of stress strain behavior compared to steel, but steel becomes also a quite difficult material to solve for it every time. So two things happen to steel and also to other structural materials when they're exposed to fire. One thing is their Young's modulus or their stiffness decreases. At the same time, their yield stress will decrease. Okay? And they will start decreasing at different temperature levels and at different rates. Okay, and Eurocode has, and also I think now ASTM also has let me show you the graph first. They call it reduction factors at every given temperature of the structure. So let me actually try to show it over here. So we have KE that represents the reduction factor for elastic stiffness. You can see at around 100 degrees, up to 100 degrees, everything behaves as it is at ambient temperatures. After 100 degrees, the stiffness will drop significantly up to 400 degrees, and then it will vary and it will sort of reach almost to zero at around this temperature. So we're basically saying at around 1000 degrees or so, we don't have any stiffness left in the steel. So we cannot really solve a numerical problem after that. So we have to make sure that we are bound to 1000 degrees or so. But the yield stress actually will stay pretty much the same until 400 degrees. Up to 400 degrees, the strength design that you do will remain exactly the same for fire conditions. So this is a good thing. But after that, it also picks up its reduction all the way to zero up, when it reaches 1000 degrees. This intermediate step here is called KP. It's called, the notation is proportional stress. And the proportional stress is when steel becomes, or it starts to behave nonlinear. Okay, so let me show it here. This might be a little bit exaggerated, but you can see that at this point, at high temperatures, the Young's modulus is also constant. Okay? But then it becomes nonlinear and it reaches to this strength level. So this part would be actually called proportional stress. So proportional stress is the level up to that level, the steel actually has a pretty much constant Young's modulus. It could be a reduced Young's modulus, but it's at least constant. Meaning that up to that moment, you can actually do a linear design. You see what I mean? But after that, it becomes, this elliptical shape. So the tangent modulus changes every time. So you need to make sure that you capture that tangent modulus. So when you plot the stress strain curve for different temperatures, you see that, assuming that it's behaving elastic perfect in plastic, well, in reality, there will be some strain hardening, but let's assume it's behaving this way. Up to 100 degrees, nothing really changes in terms of stress strain behavior of steel. But as you go higher up, you can see up to 400 degrees, you have this nonlinear shape, but then it reaches to the same stress level, yield stress level as before, but then it drops significantly. So you're dealing with a different material at every time step. That makes fire engineering, structural fire performance or analyses quite difficult to. Even the simplest versions that we will do here, simple supported beam, incredible simple structure, but still it becomes a highly nonlinear problem. So here is the thing that I try to mention. This part is also related to P delta effect. So we have a very highly nonlinear material. We have a behavior that is composite in nature. We'll talk about that, but maybe it's something that I need to touch upon right away. So imagine that this is your steel structure, cross section, and you're exposing it to heat, and you would expect, because there's concrete on top, that the temperatures will be here lower than the temperatures underneath. So that means when these temperatures are lower than this material actually, essentially, mathematically speaking, is a different material than this, right? So that means you are essentially solving a composite cross section. Even if it's homogeneous, it's steel. if it has different temperatures across the section, you're solving a composite material. And that's the reason we will always talk about the fiber approach, or trying to divide this cross-section into different small, preferably rectangular sections. At each little section, we assign it a different Young's modulus, a different stress strain behavior. Okay? And this is called fiber approach. And this approach is not new. We just adopted it from mostly earthquake engineers, mostly reinforced concrete people. And it is widely accepted in OpenSees, as you might already be aware. We're just adopting that behavior because in our essence, it makes sense to treat it this way. Any questions? Okay, let me talk about demand versus capacity. So here things get quite interesting. So the blue curve is your resistance. This could be a resistance of one element. It could be a resistance of the entire structure, depending on how you how you look at it. But we know that when we have a fire, the resistance will drop because the yield stress, as well as the stiffness of the material, let's say it's steel, it drops. Okay, your resistance could be related to yield, or like a purely strength problem, or it could be related to stability problem, which is Young's modulus. It's related to stiffness rather than the strength, right? So depending on whatever your resistance is as a function of, it will drop when the structure is exposed to fire. And this is the x-axis here is time, but you can think that as time increases, the temperatures also increase. So this is the blue curve. But when we have applied enough heating and then we start to cool the structure, or the structure, the fire is extinguished and the structure cools itself off, very, slow cooling phase. And then obviously we, for steel and for many other structural materials, we want the strength and stiffness to be regained, okay? And that's usually what's happening in terms of material. So we will get we will get increase in the resistance. Probably not back to normal, because there will be some permanent deformations and damage, but we are seeing this pickup. So let's look at the demand, which will be a non-zero number in the beginning, because you have a gravity loading on the structure. Okay, and that will be maybe in the beginning it will be constant for a while, but when the temperatures pick up, we get this thermal induced stress, as we talked about, because of the boundary condition. Nothing is free to elongate, right? You cannot build, as you guys know, isostatic structures. Isostatic structures they can observe the free stress or elongation without creating mechanical stresses, which is great for us, but you cannot create isostatic structures because they're not redundant enough. They will collapse if one of the boundary conditions are damaged or something. So every structure that we build is hyperstatic, meaning they have a remaining degrees of freedom that we need to consider, and that makes this induced demand happening in any structure that we apply to fire. So we will actually get a pickup of demand at some point, and that will peak at some point, because in the end, the yield stress is also dropping. So the capacity of the structure is dropping, and that way the demand is also not, at some point it will level off, and then it will start to drop as we go to cooling, because now the material contracts, so that thermally induced force will drop to zero or almost to zero. So we have this dynamic behavior of demand and capacity, as you can see in a very simplistic curve. And this time when these two things intersect each other, as you guys know, demand intersects resistance, that's the critical time. That's when the material, when the structure fails, right? So when resistance goes at or below the demand, that's when the resistance, when the structure fails. So we call this as a critical time that we need to calculate, or it could be also related to temperature. critical temperature. Either way is fine because we know which temperature is a function of time, so we can go back and forth to those parameters. Any questions about this? Okay. So we have the demand, which is related to gravity, that stays constant pretty much. But then we have an additional demand that could be a function of the Young's for moment of inertia of the cross-section area, Young's modulus, yield stress, the increase of the temperature, the rate of increase of the temperature, or the thermal gradient, we'll talk about that later, and of course, the boundary conditions. It could be a function of all these happening simultaneously. This is real behavior, but what Eurocode does assume, which is also the sort of the assumption that American codes adopted, is, hey, this change of the demand is a fairly complicated phenomena. You need nonlinear analysis, and it's very case specific, right? It's case specific. You can see it's a function of all these things. So why can't we do? Why can't we assume just demand not conservatively, but we assume that the demand stays constant. Whatever the gravity that's loaded initially, it just stays constant throughout the entire fire duration. Not correct entirely, but sometimes for many problems, you need to obey this type of ruling, at least to get an understanding of what type of critical time that we have for that structural element or for that entire structure. Okay. So again, this is what you can do in analysis. This is something, it's code-based, which is still something that is being widely accepted. But the resistance, it's changing. Resistance, we can calculate that with our analytical approaches. So we don't need a computer program to calculate the drop of the resistance. All right. So I will go through how we calculate the axial load capacity and how we calculate the bending capacity of the typical beam, because in the end we will be solving a beam. But similarly, you can think of this as a column. Actually, in every structural fire problem, a beam is not a beam, a column is not a column, everything is a beam column. Okay? Just think of it that way. You will never have, unless you have a free roller support, like free boundary conditions, a beam will always pick up, or let's say horizontal members as well as vertical members will always pick up axial load because they are being subjected to fire and they will elongate or contract. So now I'd like to make a distinction between uniform temperature distribution throughout the entire cross-section and a non-uniform temperature distribution across the cross-section. And I call it thermal gradient being equal to 0 if it's a uniform, thermal gradient being equal to non-zero if it's non-uniform. And in this sense, it makes actually the problem much more complex when we have nonlinear temperature distributions. From your mechanics class, if your cross-section is symmetric, if your cross-section is homogeneous, you know that the geometric center of the cross-section is in the middle, and that's also equal to your location of your neutral axis or elastic centroid, as well as plastic centroid, right? Elastic centroid is the weighted area, so basically solving this integral, but we know that the Young's modulus is everywhere constant, so it's pretty much centroid of the area is equal to centroid of elastic centroid, as well as plastic centroid is when the entire cross-section has yielded. That also stays constant because yield stress is constant throughout the entire cross-section. So everything is in the same place, assuming that that your cross-section is homogeneous and symmetric, and axial force will act on that at that geometric centroid. This is the bottom temperature. This is the top temperature. You can see it's uniform. So it doesn't have to be at ambient temperature. It could be 400 degrees everywhere. It could be 600 degrees everywhere. As long as it's uniform, these rules apply. And then you can see the yield stress also being pretty much constant throughout because we have a constant temperature. And the capacity is calculated as taking the yield stress outside of the integral because it's constant, but keeping the reduction factor of K inside the integral
and that could be just one number. And then, of course, since this stays also constant, it basically the capacity at fire conditions for load or for axial load is just multiplying stress times area by this reduction factor. That's it. That's the only difference that you have from ambient design to fire design for uniform temperatures. For non-uniform temperature distribution, so you have the bottom flange, assume it has a higher temperature than the top flange. So let's assume it's a linear variation, it could be anything. But the stresses will be mirroring that, right? So it will be reversing because now you have low temperatures equivalent to higher stresses or the stresses which are not reduced as much. And high temperatures are equal to lower stresses. So you have higher strength in the colder regions, cool regions than the hot regions, okay? So it will be mirroring this temperature distribution. And let's look at the capacity and let's talk about this in a minute. So the axial load capacity with respect to fire is again, the yield stress could be kept outside. This could be the yield stress at ambient temperatures, but this integral, you cannot keep the Ky outside because it will be changing at every different fiber that you deal with, okay? So, and you can, make this integral as a summation because you're dealing with fibers, which hopefully have the same area. So you can just sum them up instead of running the integral, okay? So the fiber approach gives us this formula where now you're actually taking, basically taking the weighted area of each strength reduction into the summation. Okay. So you need to do this calculation. So the geometric centroid is not changing throughout the entire analysis because you're not changing the cross section. But the elastic centroid, which has to do with Young's modulus reduction, as well as the plastic centroid, which is this here, is shifting up, not to the same location necessarily, because the reduction factors are different for stiffness and strength, but they are shifting up towards cooler region, okay? And what does it do? It basically shifts up this axial load either to the plastic centroid or elastic centroid, wherever you are in your analysis. So it actually induces additional moments in your cross section because you're now, the concentrated axial load will be acting at a different place than the geometric centroid. Let's do a very simple example. We like to calculate the axial capacity, the location of the elastic centroid as well as plastic centroid of a rectangular steel section with non-uniform temperature distribution. Assume that we don't have this I-beam shape. Let's assume we have a rectangular solid section. Okay. So it just, the depth is D, width is B, so we can just calculate it correctly. And the temperature distribution is 700 degrees at the bottom. It's composed of 4 layers or 4 fibers, and with the same equal area. And then on the top, we have a temperature that's equal to 100 degrees. So the temperature gradient is quite high here, as you can see. So the axial capacity formulation is a summation, and you can just put this on a spreadsheet. It's quite simple. So you put the areas of each fiber, you put their locations with respect to a reference axis. In this case, it's going to be the bottom is going to be the reference axis. And then these are the locations of the centroid of these layers. So the first location will be here. The second one will be here. Third one will be here. So you're looking at the geometric centroid of these fibers. And then next, you interpolate the temperatures as sort of assuming that, that fiber will have a constant temperature throughout. So there's an assumption here. And then yield stress reduction as well as stiffness reduction will be calculated separately. And then you go ahead and calculate that how much of an axial load if one fiber can carry. And then you just add them up in order to get the entire capacity of that cross section. And we are assuming the yield stress is equal to 275 megapascals. Any questions with respect to axial capacity? Okay, once we're done with these examples, maybe we can take, I don't know, maybe 5-10 minute break, and then we'll continue with, as long as you guys follow. Okay, this is exciting. Well, at least to me. Hopefully, it's exciting to you too.
Just keep an eye on the clock too.
Oh yeah, 11:20. Okay. So the bending capacity here, it's for uniform temperature. Again, geometric centroid, PNA and NA will stay at the geometric centroid. The PNA is evaluated, as you guys might know, that the net axial load should be equal to 0, but it should be divided into, the area should be divided into 2 equal tension and compression. But it's not exactly the same when we do apply the non-uniform temperature distribution. Okay? Now we have to put the KY inside of that summation, and our PNA actually shifts again up to a cooler region, because that cooler region can carry more load than the hotter region. Another example that, you know, this is already being distributed to you, so you can look this up more in detail in your spare time. But we can calculate the location of the PNA as this, and we already calculated the geometric centroid as well as plastic centroid. You can see that 3 of them, although close to each other, they're at different locations than the geometric centroid. So that makes our problem quite significant at early stages. One more thing that I'd like to mention before I continue to OpenSees is this beam column behavior. As I said, beams and columns, they will always act as a beam column. So in the end, we have to look at its capacity, looking at this PM envelope. Okay? And because we have this axial load shifting towards cooler region, I mean, you can think of this as a column, and the right-hand side is subject to the higher temperature than the left-hand side. So the axial load, let's say it's the plastic centroid, is shifting towards the cooler region. So that axial load actually will induce more moment if we're calculating the moment about the geometric centroid. Most of the structural analysis programs, they calculate the moment at the geometric centroid of the cross-section, because that's the one that's not changing throughout the entire analysis, unless you're, you know, sort of changing it, adding a plate to it or something like that. So, and you will see in your structure behavior, when you look at that envelope, that additional moment decreases the capacity, or it shifts the PM envelope in a different place whenever you have non-uniform temperature distribution. So this black PM envelope is the one that's at ambient temperature, or any temperature that's uniform. It could be 400, 500, because you can see it's normalized. So it will always stay in the same shape if we have uniform temperatures. But if you have a non-uniform temperature, you have this extra moment that's being induced to the structure. So this envelope, which you see in red, will actually shift, or we call it distortion of the envelope. So what does it entail? So if you have a PM combination of your structure happening right here, okay, according to your traditional design, you have to say this is fair, right? It's outside of your envelope. But it's essentially, if it's a non-uniform temperature distribution, it actually not failed. It has some spare room. Vice versa, if your PM combination is right here at any instant of your analysis, according to your traditional design, you're safe. But actually, in reality, you're not. You have already failed this. So when you're designing your cross-section, or especially that it could develop non-uniform temperature distribution, you have to take account of this shift. And that shift is changing at every time step. Or let's say it that way, at every different temperature level, thermal gradient might be different. So this shift is actually happening at every time step. All right. Let's go to OpenSees. OpenSeesPy, it really is, I mean, I've seen Francisco's talk last week, and I think you guys are now familiar with much more complicated structures and distributed plasticity and analysis procedures. Things that are really different in this simple fire problem are these four following things. One is the material. So instead of steel 01, right now in OpenSeesPy, we have only one available. There are actually multiple things, so I'll talk about that later. But steel 01 thermal is the material library that we built. We built that library so that it takes account of that change in the stress strain curve of the steel with respect to temperatures. Fiber is there. Fiber thermal is the one that we will use that takes account of that Young's modulus and strength of each fiber and calculates it for each fiber. Element type, displacement beam column is there. We just added thermal. That takes account of that temperature effects. And lastly, in loading conditions, this is brand new. So instead of applying, a typical load, concentrated load, moment, uniform distribution, distributed load, you apply a temperature at different. So this is basically, this basically says the element is beam thermal. It is subjected to 500 degrees at the bottom fiber, which is this is the location of that bottom fiber in the cross section, and 30 is the degrees of Celsius that you apply at the top fiber. So there's a large thermal gradient, and you can apply this load right instantly. You can do it incrementally, so it ramps up. All right, so the validation. So what we're trying to do here is we're going to validate. We're going to use two separate scripts, which are already on your Colab. One is validation, and the other one is validation 2. Validation, this one basically has one element, 2 nodes, and we just want to make sure that our material elongates as we have exposed it to the Eurocode elongation graph, and that graph is that one on the right. And we should be getting something quite similar or exact actually when we elongate this beam freely when we are subjected to temperature. Okay, so and the material properties that we give is 400 gigapascals in Young's modulus, 355 megapascals of yield. These are not really important because we're not actually subjecting to a stress here. We're just letting the pin roller element elongate by delta L when we subject it to a very high temperature incremental. Okay, let's do the demo on the road. Okay, so validation 1. Let's go through this together. So first we install OpenSeesPy as well as the visualization, OpenSees visualization module. Let this run. So you can do this run all as well, but let's go this together. And then you import OpenSeesPy, the visualization, and MATLAB, Matplot library, as well as NumPy, which is the number or calculation equations that you require for the OpenSees. Now we go to building our model. We start with wiping it and creating a model that has 3 degrees of freedom for each node, but it's in 2-dimensional space. And then we have pretty much 2 nodes, 1 meter apart from each other. It's a horizontal beam, and that one node is fixed in all degrees. Well, in 2 degrees of freedom, it's free to rotate, but it doesn't really matter that much. And then the other one is the second node is a roller. Okay, we create that. When we get to material, we assign a Young's modulus, yield stress, and this strain hardening ratio. This is basically the slope that you have seen previously. And we apply that. we do the transformation as well as we, you have to do this for any work that you start with OpenSees. Here, we can do co-rotational, but it doesn't, in this case, it's just going to be, it's not going to be nonlinear problem, so we can leave it at linear. Here's the deal. So you need to create a fiber. That might be new to you. I don't know if the previous OpenSees examples covered that. But we have, you can create your, like there's a function that does that, but the parameters that you have to give are these. And let's go through them together. This is very, very straightforward. So any I-beam, and this creates an I-beam rather than just a rectangular block. You need the depth of the beam, you need the flange width, you need the flange thickness, and you need the web thickness, okay? 4 geometric parameters. And then you need to define how many divisions or fibers do you need along those parameters, okay? NFDW is how many divisions you want throughout the web. And let's see it here. So not the depth, but just the web. So I need for this one, I gave 9 of them, I think. 1, 2, 3, 4, 5, 6, or 11. Let's look back. But it's basically the number of divisions that I want throughout the web. And the next one is number of divisions that I want, or fibers that I want through the web thickness. So here you can see it's only 2. And the next one is number of the fibers that I want throughout the flange width and throughout the web flange thickness, okay? And then this calculation is done automatically. So when you give these 8 parameters, it just calculates the depth of the web instead of just the entire depth. And then does basically calculations for each rectangle, which is the fiber. And then this one we will be able to, this is a this is a list that you could create in Python that actually enables us to visualize what we have created, okay? So we basically said that we want 14 divisions throughout the web, 2 divisions throughout the web thickness, 10 divisions throughout the web, the flange width, and 2 divisions throughout the flange thickness. And this is what we have created. So if you change these parameters, you can visualize that you have done it correctly, okay? So I think we run this already, right? Okay. And then we visualize this, but we didn't actually create the section yet. Let's create the section. Again, the section is going to be composed of quadrilaterals. So it's rectangular sections, and it's going to be fiber thermal, okay? And these just are for, different corners of that element. We patch it. And then now we're defining the beam elements, how many integrations points that we want along the beam. And in this case, we can just keep it as 5. But, for this problem, it doesn't really make a difference. And then we create our element. Our element, there's only one element. It's called beam displacement column thermal. We have 2 nodes, 1 element. We hit this run. We like to visualize our element as well. Unfortunately, we can see the nodes, but not the element, because OpenSeesPy doesn't, the visualization part of it does not recognize this displacement beam column thermal yet, but it is there, trust me. Okay? So there should be 1 element so if I just change this displacement beam column, which I want here, it will actually show. But you can see the boundary conditions. Now is a thermal load. So what we try to do is, again, as we before for earthquake analysis, we try to we create a time series, which is going to be linear in our case, and then we create a pattern. It's going to be plane, similarly like you have done for other work. And now we're going to create a load, which is in terms of temperature, and subjecting it at different fiber levels. So we are basically subjecting 2 fibers, bottom and top, to 2 different temperatures, and everything in between will be linearly interpolated, okay? And you can actually put more here. You can define up to 9 different
fiber locations where you apply the temperature distribution, which could be important. But this time we're just thinking that this is a linearly changing temperature distribution. I think I've shown it somewhere in the before. So I run this. And then I define my analysis here. So I will be increasing this temperature up to 1180. So that's like up to maximum capacity of the steel material. But again, this is not a structural problem. This is a thermal elongation. I just want to see that entire range. And then I hit run here. I do it incrementally up to 100 increments. I hit run. So now it's increasing it, each time step, and then it gives me this plot. Okay, and that's the end of this validation. So if you look at this plot, and if you look over here, you can see that it mimics it exactly. So we are good with the first validation, which is the thermal elongation. The second validation we'll do is, are we capturing the stress strain behavior at elevated temperatures correctly? And I'm going to run again this quite quickly, and then I move on to the exercises. Great. Do they have time on Friday as well? Okay, good. Just I always want more. If you guys taken my class last quarter, it was always running late, I guess, right, Safa? Just don't get this opportunity that much, so I'd like to put everything in. So we're putting the same thing. We're wiping the analysis. Now, again, we have the same geometry, same material. Here, now we have to change this to co-rotational because we expect a nonlinear stress strain at elevated temperature. When we do linear, this doesn't work. Again, the same cross-sectional geometry, nothing really that we need to change here. So we assign that section, we define the elements. Start all over. Fiber section. Okay. Now, let's apply the load without applying any temperature to it. So I'm applying a load that is, it's basically, if this is a pin roller, I'm applying load here in tension. Okay, that's all I'm doing. I'm incrementally applying that load. I should get a quite linear response. And here we go. It's a linear response with some strain hardening. Okay, so now I'm gonna save this. And I'm gonna go back, and I might be doing too manual, but I didn't figure out how to do it otherwise. I'll go back and rerun everything. This time I will skip that gravitational loading in the beginning. I will apply the temperature first, and then apply that tensile load, and see if I'm doing this right. The stress strain behavior or load deformation graph that you see will be different this time. So I'm skipping this loading, and I'm just jump to fire loading. This time I'm loading up to 400 degrees. Okay, I don't want to load at 1000 because then I won't be able to carry any load. And then run the analysis, and you can see now my thermal elongation plot will be only up to 400 degrees. Okay. It's still thermal elongating, still free restraint. So I'm not building any stress first. Now I'm applying the load. You see, now I get a highly nonlinear load deformation graph. So I am basically measuring a displacement, well, the axial deformation of this element, as well as the axial force that's on this element. There's only one element, and that's what I get. So a completely different stress strain curve. And then I can just compare them to each other. First of all, you'll see that it actually stops converging at some point because it's highly ductile at its stage. Second of all, it shifts. There's a shift between those two, and that's accepted because the first one, we didn't apply any thermal elongation. The second one, we applied a thermal elongation. So it actually starts with some deformation, stress-free, but it is a deformation, and then it moves on. So you can see here that our material also behaves as we want it to behave. So these are the two validations. Any questions? Okay. Let me go now to the main exercise. This will be also, somewhat simplified form in terms of temperature development as your assignment. And we will go through this together here too. But the coding would be up to you. So we'll share the validation 1 and 2, and then by tweaking a couple things there, you will be able to run this analysis. So what we're dealing with here is the beam, a simple supported beam composed of 10 elements, which has first of 3 different boundary conditions: pin roller, pin, and fix. Quite easy to do this in the script. Subjected to 10 kilonewtons per meter, uniformly distributed load, subject to the fire underneath, okay? As you can see, and then the cross-section that we're dealing with is IPE 330, which is the same cross-section that you dealt with in the validation part. So the cross-section is not changing. We assume that there is a concrete on top, which is typical for a composite, a beam construction. And that concrete on top will actually create a non-uniform temperature distribution across the cross-section, because it will actually sink the heat, or it will act as a heat sink, and that will lead to lower temperatures in the top flange than the bottom flange. In reality, OpenSee's fire module can actually do, with the tickle form coding, it can actually do the heat transfer analysis as well. Okay, it can do the heat transfer analysis, store all the temperatures in each fiber, which could be temperature and time dependent for any fire curve, okay? And then apply it to the structural analysis program. But in OpenSeesPy, we're not there yet, so it's going to be a simplistic version. So what we're going to do is we're going to take the results from the typical code and simplify it. I'll show that to you. But now let's assume that we are subjecting this beam to this standard fire up to 30 minutes. So up to 842 temperature or degrees of Celsius, and in a nonlinear fashion like this. So it will be a different time step at each step. And then we look at effect of boundary conditions. We're looking at cooling effect. Once we heat up to 850 degrees of Celsius, we will let it cool for another 90 minutes and see what kind of things that we do observe in terms of 3 different engineering parameters. One is the axial load development in the beam. The other one is the moment at the midspan over here. And the third one, or the first one, is going to be the vertical deflection at the midspan. So we're going to look at these 3 different parameters. And we're also going to look at what if instead of 10 kilonewton per meter, which is 20-30% utilization ratio of this beam, what if we apply 1/100th of it? Okay, so we have a much lower gravity load to begin with. And this could be actually detrimental to the stability of the structure, because you're compressing it and it's almost straight. So you're not getting these vertical deflections to offset that compressive load. We'll talk about that too. So first, the heat transfer analysis. This again could be done in OpenSee's different executable file that you can get from the website. I'll talk about that also as well. But the evolution of the temperatures up to 30 minutes are shown here with the cross section. So we'll start at around 20 degrees of Celsius, and then at
5 minutes, we have a temperature distribution throughout the fiber like this, okay? Lower temperatures on the top flange and higher temperature on the bottom flange, and actually high temperature in the web as well because the web is very thin. And then we get up to 10 minutes, 15, 20, 25, and 30. So this is sort of the last phase of the heating, okay? Any questions here? So you can run a typical heat transfer problem either on OpenSees or anywhere else and get these temperature gradients, so to speak, for each fiber in the beam.
Serdar, just to emphasize from students too, that on the whiteboard over there, that temperature curve, that's something that if you think in terms of other loading cases, that's like the applied loading, if you would. Like and in fact, the Eurocodes have it, and in the US, it's not in our codes, but there's guidelines that say you take the heat content of a room, like what can burn, and certain information on the circular, how open the circulation is, how much air can you do, and so forth. You can develop that time temperature curve for the temperature in the room. And then what Serdar is showing here is the temperature in the steel. And so what has to happen is that the temperature in the room from the gas has to go kind of through the thermal insulation, and that's using the differential equation. And then this is what's ending up in the steel.
Correct.
So, if you think of it in terms of what we did with ground motions and things like that, seismologists do, all the seismic hazard analysis, and then we get a target spectrum, and then we pick ground motions, and we take it from there. It's kind of like the building code provisions, if you will, in fire engineering, you give the time temperature curve in the room, and then kind of you would have to take it from there. Now this thermal transfer, that's in, I guess, the tickle file, which we don't have in OpenSeesPy, so we're going to simplify this a little bit. The idea is these temperatures here are the temperatures resulting in the steel from that time temperature curve on the black and the white.
That's exactly correct. Thanks. So basically, the gas temperatures are like sort of the ground motions that we experience, and then from the gas temperature to structural temperatures and cross-sectional temperature distribution, it's like the spectrum that you use. So how the ground motions are affecting a particular building with a particular period. It's the same thing going from gas temperatures to structural temperatures. But this is what we need for the structural or thermomechanical analysis. That part could be developed somewhere else. For now, we're just going to use standard fire, but it could be any type of fire curve if we know the fire loads and the ventilation and the compartment dimensions of a building or any structure. Let's look at first of the effect of the importance of restraints. So if this was a pin roller, okay, and it's subjected, pin roller beam subjected to 10 kilonewton per meter load, you would expect that at some temperature, at a very high temperature, the resistance is going to drop and intersect the demand, which stays pretty much constant, right? 10 kilonewton per meter. And the beam is going to fail in runaway. And that's exactly what's happening when you look at the red curve. It just does this with a section temp. So these are the temperature. This is the average temperature of the cross section. As it increases, the deflections and vertical at the midspan, the vertical deflection is increasing, and then at some point it just goes boom, and that's when the OpenSees analysis actually stops to converge. And Eurocode, just as a side note, you can do back of the envelope calculations and find out the critical time to be equal to approximately 700 degrees for this particular problem, the cross section and the length. And you can see that the analysis is not too far off, or vice versa. The code is not too far off to calculate that runaway behavior. But when you just change only one thing from pin roller to pin on one boundary. So now it can develop compressive stress inside, but also if it goes runaway, it basically stops this beam to fail in runaway motion because it's being held by these two supports now, axially and vertically, translationally. Right. So you can see that you get more deflections because there will be a compressive force that's actually developing, and then it's actually pushing the beam down. The more deflection, vertical deflections, but in the end, it will actually, continue up to a point where the material cannot carry anything. The material properties drop significantly, but it doesn't fail. Okay, so changing one little thing, just the axial restraint in the beam, can actually make the beam stay longer as long as the connections are strong, which also is a big problem in this type of analysis. This is just to show you the change of the axial load, deflection, axial load, as well as the midspan moment behavior or diagram throughout the entire beam. This thanks to Brian, who's a graduate student here. He had this code for his own research that can just collect the history of the axial load, moment, whatever internal force that you have. So I gave him the results that I got for this for this problem. Okay, pin beam with 10 kilonewtons per meter load subjected to fire, and he was able to plot me the changes, and there will be some takeaways from this. So first we'll look at the deflection. So he just made a video of it. So as the time goes, the beam will deflect, as you can see. It's held again by these two supports translationally, so it will deflect a significant amount. P delta effects are there, and the second part you will see the axial load history of the beam as it expands. And this is, mind you, this is all heating. Nothing is cooled here. Everything is up to 30 minutes of heating. And you can see here it starts with a very large compression, and that compression force gets to zero, and then you get some tension in the beam. That's interesting, right? It's quite counterintuitive if you think about it. You're heating the beam, but the vertical deflections are so excessive, more than the heating or the thermal elongation to catch up. So you're developing catenary action, or let me actually stop here. Catenary action in the beam into tension. So you're still in the heating. Now, the next step would be looking at the shear diagram of the beam. You guys know this is a uniform distributed load, so you have a linearly changing shear diagram. Is this? You can see it's not changing at all because the gravity is not changing. The shear diagram will stay constant pretty much throughout the entire fire duration because you're not really changing the gravity. This might not be the case for a column. The third one that he looks at is the midspan moment. Obviously, WL squared over A in the middle, and then you can see the moment is also reducing almost to zero. So what does that mean? Beam acts like a cable. No bending, almost no bending, and it's in small tension. And this happens during the only heating phase. It's not cooling. So beam starts to hang from its supports, and that makes the support conditions very, very important. Yeah.
You're modeling this. Is this what you modeling with one element?
Oh, these are 10 elements. Yeah. This is now the validation was just one element. Now we're looking at the entire span, and we're using 10 elements here.
It just occurred to me, like shear diagram. If you think about a catenary, what happens is what was shear in a horizontal beam, the vertical component becomes part of the tension in the catenary. So I would think that the shear would similarly follow the moment go to zero. I mean, that you still have that load over the span, but just as the moment disappears, the shear would similarly.
I think the diagram shows the global. So I think he ticks up. He makes a tick here to global. I believe so.
Okay, yeah, it transformed it.
Yeah, just to show. Yeah, because you're right. The deflections are so excessive that you need to look at it locally if you just want to, understand the capacity. But just to show, like overall, the shear is not really changing. We change it to global.
Yeah, if you think of the shear as being a result of the vertical component of force, yeah, that's not changing.
Yeah, that's good.
Yeah, we did a little bit of thermal loading in linear analysis class, and a lot of our intuition changes.
Exactly. You got to think outside of the box, really. All right. Let me see how we're doing in time. I think we are going to be okay. If not, some of the coding might go into the second class. So we have this might look a little bit, all around, but let me show you what this graph shows. So this is the axial force that's going into very maximum compressive force, and then it starts to reduce, and then you can see the tension over here. So left-hand vertical axis is showing the axial force. The right-hand one is showing you deflections. So this red curve shows deflections, which they just basically gradually increase. And I shown this together because you can see the effect of deflections on the axial load behavior a lot. So just mind that the axial capacity of this beam at ambient temperatures is about 2,223 kilonewtons. So we're not tapping that at all. So the beam has not yielded in axial load for this 30 minutes of fire loading. Okay. So what happens in the beginning is that Young's modulus and yield stress starts to drop actually after this. So the Young's modulus will drop after 100 degrees of Celsius of the structural temperature, and the yield stress will drop at around 400. And then you will get this maximum axial load, and then that axial load will start dropping because the deflections are getting excessive, not because you started healing. Okay. And then so this is the reduction of the yield, and the last phase is when you get into the tension. Again, the beam acts like a cable hanging from its supports during the heating, because the deflections get much more excessive, or the rate of deflection is much more than the rate of heating or rate of elongation. Okay, so that's what defines this catenation. When you look at the moment behavior at the midspan, you start with some moment in the beginning, right? Because that's loaded with 10 kilonewtons per meter uniform distributed load. And the moment is counterclockwise, and it's actually getting higher. So you see this thermally induced moment counterclockwise higher up to a point where it reaches maximum. This increase is due to this axial load, that shift of the axial load resultant that's acting on the centroid towards the cooler region. That actually adds additional moment to the beam at the midspan. And you can think of this as not just the load shift, but also the P delta effect. Those two things acting together to increase that shift outwards in the beam. And then when we get reduction after 400 degrees in yield stress, obviously the moment starts to drop, and then almost to zero when we have the beam hanging at the supports. If you look at the plastic moment capacity at ambient, you can see that it's actually very close to the plastic moment capacity of the beam before it starts to do reduction of it, and that's why we get this reduction, because it's almost at its capacity in terms of plastic moment. The takeaways from this is axial load reaches maximum before Young's modulus or yield stress starts to drop. So axial load is a geometrical problem in the beginning, rather than like how things actually deflect vertically, rather than being a mechanical problem. The second one is a midspan moment increases due to elastic or plastic central shifts towards the cooler region, plus the P delta effect. So those two things act together to add additional moment to the midspan, which is the worst case at the midspan. Towards the end of the heating, the beam hangs on its supports like a cable. Tension is there, and also a very small moment, so no bending. And here the connections become quite critical to design. So boundary conditions. So we already went through the blue one, the pin, as well as the pin roll. Sorry, when you do fixed, you get a smaller deflection, which is understandable because the rotational capacity here is, much more. The resistance in rotation is much more. That decreases the deflection that this beam is
exposed to at the midspan. In terms of axial force, you get, because the deflections are limited in the fixed beam, you get a much larger axial force. Still not there in terms of yield stress, but it's there. You see, it's much more. So the takeaway from this would be, due to less vertical deflection, the fixed beam develops more axial load. And you can see that there's no axial load in the pin roller, as expected, right? The pin roller is free to expand. When you look at the moment development at the midspan, you see that we started at 100 for pin. Obviously, the midspan moment for a uniform distributed load of fixed beam is equal to WL squared over 24, right? And WL squared over 8 is 3 times larger. So that's where you see in the beginning the difference to start with. But then you still get that increase of the beam midspan, but this time, I mean, obviously you don't reach as much of a midspan moment because initially you have started with a smaller bending moment. And then when you look at the pin roller, you start at 100 as before. That's not changing, but it stays almost constant until runaway behavior occurs. Okay, because the gravity is staying constant. So you don't have these thermally induced moment when you experience it in the restraints. Lastly, we can also look at the stress development in the fibers. Here you see the bottom fiber at the midspan, this one over here, and the top fiber. When you start with 100 kilonewton meter midspan moment, it's counterclockwise, meaning the bottom fiber is in tension, the top fiber is in compression, right? You see that right away, and they're almost symmetric. And then you get more axial stress, pretty much in tension in the bottom flange, and then more in the top flange when the axial load is increasing here. But later on, there is a funneling behavior, basically because of the yielding reduction. You get less and less stresses developing in the beam, where towards the end, as you would expect, the moment gets close to 0. So the difference between those two gets close to 0. When you look at the stresses for a fixed beam, we can look at the stresses at the midspan as well as at beam end. The takeaway from this would be the yielding in the beam end, bottom flange, and the midspan, top flange, it's critical. And the deflections are limited for a fixed beam, as we have seen before. The entire cross section is under compression in the very early phase. You can see that none of the top flanges are in tension in this. Bottom flanges are in tension. This one, if you look at this here, the bottom flange is in tension because the moment is counterclockwise. But here they get actually into compression, all of them, because the axial force actually dominates the stress behavior in the cross section. So you still get moment. There's a difference, but that it's always in the compression phase. This is something that also is quite important to take away. 3 different videos that I will show, and start with some of the assignment work on the board. So here's the thing that I previously talked about. Here's a PM envelope. So what we're going to do here is we're going to look at pin roller, pin, and fixed beam. And we're going to look at axial load at the midspan, well, anywhere in the beam rather, and the moment at the midspan. And we're going to record those P and M at every time step as this little dot, how this little dot starts. And we're going to see how that progresses within this PM envelope. Again, the black one is ambient. And this red one is, we're not going to be changing it every time. The red one is sort of the end of the 30-minute heating, end of the analysis, okay? So we're going to make sure that if these dots are crossing the border, or if they do, does it mean it fails, or vice versa? So this is pin roller. What do you expect the moment to be at pin roller? Any guesses? We apply a load to pin roller beam. What happens to moment at the midspan?
stays constant, right? What is the axial load in the beam as the fire develops in the beam? It's a pin roller. 0. Axial load starts from 0 to always 0, and then bending moment will be. So you can see that bending initially it's basically just it basically its bending moment is 0, but when you divided the bending moment capacity, it gets higher and higher and higher. So we get a horizontal movement in the beam until it basically fails, and this is the runaway behavior. Okay, so again, I maybe forgot to mention these are the axes of the normalized capacities. So as the if the temperature increases, obviously plastic moment capacity drops, so you get this horizontal movement.
This image is not showing like the blue one, for example, should be shrinking, the yield surface should be shrinking.
Yes.
Because the moment's not changing, like you said. What's changing is the MP. So we're looking.
Yeah, we're not getting the shrinkage because that would be difficult to visualize. So we're just looking at the normalized way. So the moment actually is staying constant. What's not staying constant is the moment divided by MP, which is MP plastic moment capacity is reducing. So we're getting more and more utilized, so to speak.
So that red curve that we showed here, that's the shape of it, but would the size be that bigger, would it actually be smaller? Because if it's a high temperature, would all this quantity be smaller?
This one? It basically takes the average of the midspan, the plastic moment capacity as well. So it will be this size. It won't get smaller. So the second one is a pin-pin beam. So now we have a dynamic behavior. We have an axial load that's changing. That we have a yield stress, that yield capacity that's changing. We have a moment that's changing, as well as the MP that's changing. So this is the sort of, these dots will be a combination of those. Let's see how this one is going to behave. Do you see towards the end? It actually, well, this is just a coincidence, sort of. You know, it could have gone much more, as we have seen, like the yield stress capacity was much more, but it doesn't. Here, it basically just shifts because of the deflections, but then it follows this red line, which is like, it basically is at its ultimate capacity, and it tries to continue a little bit, and then, you know, at the end of the heating, it stays on this line. So it doesn't stay on the black line, it stays on the red line, which is the distorted PM envelope. Okay, so you see that drop in the axial, like the increase in the axial load, because it goes down here, right? And then there will be also an increase of the bending moment capacity towards the right. So that dynamic that you can see in this video quite clearly. And the last video that I will show is a fix that kind of transverses everywhere this time. And then you see it bumps to the capacity, so the deflections will start changing, and then goes to the other direction, and it kind of fails again at or around the red line here, over here. Okay. So this is just the evolution of PM, and this is, I think, this normalized graphs tells us like how much of a shift and dynamic behavior that you get in this cross section. Dynamic meaning that we're not talking about static dynamics, just like things are moving and things are changing swiftly, and things are you know, shifting from deflection type of behavior rather than to, you know, strength type of behavior throughout the entire analysis. Any questions? Okay. So what I will do here is give a brief outline with the assignment. Okay. So as I said, the heat transfer model is great. You can record the temperature throughout the entire fibers, which could change. Thermal gradient can change. The
distribution can change at every time step. But what we're gonna do for this problem, we're gonna assume, as before, a linear temperature gradient. So assume that we're just dealing with the end, at the end of the heating, with this blue line, okay? And although this is the real temperature distribution, we're just gonna say, okay, this is the bottom flange, this is the top flange. We're gonna do a linear approximation, which is not obviously, very correct, but we'll simplify this heat input, okay? So we're just taking the 30-minute end of the heating, and we apply a thermal gradient throughout the entire cross section. We assume it to be constant, and we assume it to be linear, okay, the temperature distribution. And the temperature distribution is pretty much gonna look like this: 825 degrees of Celsius at the bottom flange, at the end of the heating, at the end of the analysis. And at the end of the analysis, we're gonna end up 690 degrees of Celsius at the top flange, okay?
So this is the assumptions that we will make. Let me hide this. Okay. Let's run this. We got another 5 minutes or so. I can just run the first one and show you how it's done, and then maybe on Friday we'll go with the load utilization ratio as well as like some cooling effects. Okay. So these two things are the same. We're just running. We're wiping the model. You see there's something that you need to do in your code. So you need to create a for loop or just create multiple nodes, not just 2 nodes now. You need to create 11 nodes because you have 10 elements, you have 11 nodes, okay? So here's a change. Here's the boundary conditions. Now we're gonna start with pin roller. Okay, this stays exactly the same. Nothing is changed from the validation, okay? So we get the geometric transformation here. That stays exactly the same. It's an IP 330. Nothing is changed here. Integration is not changed. Now, this part is changed, right? Now you're not having only one element, you're having 10 elements, so you're gonna create a for loop, or you're just gonna do 10 lines of coding, okay? So again, you can see the nodes, but you won't be able to see elements, but it is there. Now, previously we applied a concentrated load. This time we're going to apply a uniform load to the structure, which we do it initially as a gravity load. So we assign a UDL, which is uniform distributed load, of 10 kilonewtons. Every unit here is in newtons and meters. So this is 10 kilonewtons of force, distributed load, kilonewton per meter, I'm sorry. And that will be applied to each of the elements. As you can see, there are 10 elements, okay? And I'm gonna apply it in 10 steps incrementally. I'll start basically with 1 kilonewton and then go to 2, 3, and so forth. So this is a pin roller. You see what's happening. So we got some mid-span deflection, which is linear, nothing to be surprised about. You see the axial load is zigzagging, but it's actually, not existent. Numerically, there's some numbers there, but there's no axial load in the structure, which is obviously expected. And the mid-span moment is also increasing as we guessed, 100 kilonewton times meter, kilonewton meter, right? WL squared over 8 for a length of 9 meters. That's going to give that result. So that makes sense. It's linear. Now, after that, we're going to apply the fire load. We need to make sure that we put this here. And this is, I know that you guys know this already. You need to keep the gravity load constant throughout the fire analysis because that's not changing. So you need to put that command in order to reset the time as well as
keeping the load constant. We're creating another set of series, and we're just gonna name them two, tag them as two. But it's still linear and it's still plain. Here, instead of applying uniform distributed load, we apply it. 690 is the upper flange or top flange temperature, and it's still running. So here I'm running it in 100 steps, and that's why it's taking a little bit of time. It's also taking a little bit of time because pin roller actually fails, as you guys remember, in runaway. So it tries to converge, and you'll see it's gonna stop actually before it reaches to that level of temperature. I'm gonna do this analysis and then I'm gonna stop, I promise. Should be running. Okay, good. Okay, I think it worked. Let me see if it, okay. So it will basically plot this red curve, which you see it's runaway behavior. You see the axial load is 0, okay, and you see the midspan moment is staying constant, and that this is when it basically fails, okay. And then in the next on Friday, we'll do running for the pinned and fixed, and we'll do low utilization ratio. We're going to decrease that gravity load and look at the cooling effect as well. Sorry, I couldn't finish it. It will be extending to Friday, but hopefully that will give them a little bit time to digest. All right. Thank you, everyone. Yeah, guy would be.
They really don't know. That's we either have to just give, we have to walk through so much of that.
That's true. Especially adding gravity and then fire.
Yeah, but I think changing parameters on certain ones, that's, at least that forces you to kind of walk through.
Yeah, we'll discuss that anytime before Friday.
Yeah.
How to make it sound.
Yeah. All right. All right. And you know about the lecture set.
Yes.
That part.
Yeah, hoping to be here and then. There's a science project that my daughter is.
Oh, okay.
Scientific research.
Oh, okay. So I see.
From 5:37
Okay.
So it's, I don't know if it's there to the.
Yeah, yeah.
I don't know.
Okay, yeah.
But I'll.
Just let Brett know.
Yes, for sure.
Yeah. Yeah, sure.
Hey there.
Quick question that
Yeah,
I'm
go
trying
ahead.
to wrap my head around was this: why would the stress be greater at the lower temperature region? Like I couldn't wrap my head around.
This is the yield stress. So this is not the stress that you experience, and this is the capacity. The stress
Also, the
capacity at
capacity-
TNA.
Okay, that
So
makes
this
more
is
sense.
the status at TNA.
Okay.
When
that-
you
that makes
have,
a lot
when
more
you
sense.
calculate, so these are all like capacity problems that you need to like,
Mhm.
in order to, temperature dependent property or non-uniform temperature cases, you need to calculate the bending capacity where the yield stress actually capacity gets larger towards cooling regions.
Right, right. Okay, that makes sense. Because I guess in my mind, I guess I'll always think about this as like, the stress that the beam is experiencing. So now
Oh, yeah,
I thought
that one is gonna be, the analysis will put that in.
Mhm.
The resistance, but capacity problems that you can actually design it for. You can do it by yourself, like for fire conditions as well. It's just the demand part needs to be solved by the
Oh,
analysis.
I see.
The actual stresses will be depending on many of them.
I see. I guess like are these notebooks available for us to view at all?
Yeah. Validation 1 and 2 will be available to you. I think Greg can share that with you.
Okay.
right away. And the exercise 1 and 2, the exercise 1 will be part of the assignment, so we probably post that after the assignment deadline, like even if it's optional.
Mhm.
So basically, those 2 will be available afterwards, but those 4 of those will be available at
Okay.
the end of the class too.
And then I guess like I know you taught the fire engineering course.
Yeah.
I was unfortunately not able to take it because I had the other courses, but I'm curious like if I'm more interested in this topic, just to learn more about it.
Mhm.
Like I guess
One
like,
of the, well,
yeah,
my appointment is in spring and the summer. I'm not sure I will be teaching anything,
Mhm.
but I am here like till
Mhm.
October. So like if you want to get more information about fire, structural fire performance,
Mhm.
just email me and we'll get together.
Mhm.
I'll talk you through and give you resources, whatever you need.
Yeah, I know like a couple people that took the course and they said they really enjoyed it, and I feel like even just having that content and information to digest it would be great. And then I guess like if I like
Oh, yeah, I
if
can
you're able
share-
to share like the
Oh
slides,
yeah,
and
of
then
course. I can
and,
share my lecture notes.
yeah, that'd be great. And then if I have any questions, I can reach out while you're here and
Yeah.
not when you're
Yeah.
back.
That's all good. Yeah, just email me and I put them on the Google Drive and I share it with you. And so whatever questions that you have when you're reading through, whenever you have spare time.
Perfect. Okay,
fine,
thank you.
let me
I
know.
appreciate that.
You're welcome.
Yeah, after that,